Hello folks, this is John Buck. I'm going to work an example tonight showing you how to compute the discrete time Fourier series for a very simple periodic square wave to get an example of how you go through the process. First, just a quick reminder what the discrete time Fourier series is. We say the discrete time Fourier series coefficients, we'll call them a sub k, are equal to 1 over n times the sum as n goes from n equals 0 to n minus 1, where this capital N is the period. I should have mentioned that. So this is for periodic signals, and I divide by the length of the period, then the sum over one period of computing. Oops, I've got a new pad here and it's taking me a little while to get used to it. X of n e to the minus j omega naught n k. And in this equation, omega naught is the fundamental frequency, is 2 pi divided by the period of the signal. And again, just a reminder, this is what we call the fundamental frequency. And these coefficients tell me how much I use of each frequency. This is sometimes called the analysis equation because it analyzes the signal. So you get that down. Not having a good pad tonight. Not having a good night with writing. So this is sometimes called the analysis equation for the Fourier series. And we'll see every Fourier version we see this semester has an analysis and the synthesis equation. And the reason we call it that is this is the equation where we start with the signal x of n and we analyze it to find out the a sub k's. And as we mentioned in class, the a sub k's are actually the a sub k's are the ingredients, how much of each ingredient we need. So if we come up here, we can say that synthesis equation, if I give you the a sub k's, how do I make the signal? Well, I say that x of n is equal to the sum as k goes from 0 to n minus 1 of a sub k e to the j omega naught n k. So notice that things are a little different. In this top equation here, k is a parameter and I'm summing over n. So it's saying if I want to find, this is for a given frequency, right? The frequency of this kth component, if I bring this out over here, the frequency of the kth component is omega is k times the fundamental. So these are sometimes called harmonics. So I'm looking at saying I've got multiples of the fundamental here. Whereas in this equation, n is the parameter. If I want to find the signal at each time, this is as I said in class, the recipe. How much of each frequency, omega naught k, do I need at that time? Well, a sub k tells me how much. Okay, so that's the quick review of where the discrete Fourier series comes from. To go on to the example, I have a signal pre-drawn here. So this is my periodic square wave signal. This is actually the same one we did in class. I just have had enough questions about it. I thought it would be good to go through it again at a speed where you can all follow me or stop and look at things. So again, the first thing we need to do is identify the period. And as we look at this, it repeats every 6 samples, right? I have a period of 6 here. So I begin by saying, well, my period right? I only use the discrete Fourier series with a periodic signal. So my period n is equal to 6 in this equation. So that means that omega naught is 2 pi divided by 6, which is the same as pi by 3. And it's usually easier just to hold that aside till the very end, or near the end, to work things out in most problems. So I'll go start right in and say, well, if I want to find a sub k, I start from that same equation I had on the last page. So I'm going to say a sub k is equal to 1 over n, and then I take the sum over one period. But it turns out, as I mentioned in class and the book mentions, you can actually use any period you want. It doesn't have to just be from 0 to 6. So we often write that as saying the sum is n, is n, and we sort of put this sort of notation in angle brackets, which means periodically picking one period of n, and then the rest is the same. So I take the signal x of n times e to the minus j omega naught k times n. And for this signal, because it's symmetric about the origin, it'll turn out to be, I'll get the right answer easier by making my interval be covering that symmetry. So I need 6 consecutive samples. I'm going to choose them to go from -2 up to 3. So I'm going to say this is going to be the sum. I'll put an n now, so I have 1/6 the sum as time goes from -2 up to 3. So again, that's looking up here. So I've got 1, 2, 3, 4, 5, 6 points. Some people are bothered that this isn't symmetric and want it to go from -3 to 3. But I have to have the number of terms in the sum has to be the period. Since the period is 6, I have to find an interval of 6. I could have gone from -3 to 2. It would be fine too. Either choice is good. I just need to pick one period. And I say over that period I have x of n, the signal, times e to the minus j omega naught kn. Okay, so now I'm ready to go through and to plug in the values of x of n to evaluate this sum. So I'm going to look at the signal up here. And sometimes when you're doing this for the first time, it can be helpful to look at this and sort of write out each term explicitly, even though a lot of them are 0. So when n equals -2, I have x of -2, and I go up here and look and say, well, that's 0. So I'm going to sort of label these maybe in green just underneath to see they're not really part of the equation, but they're showing where each term comes from. So I have n equals -2. The term is it's a terrible 0. I have a 0 here. And then if I go to the next term, I'll switch over, I say I want the n equals -1 term. So in the next term, n equals I put in -1 for all the n's here. Well, now x is equal to 1. So I'm going to put that in. I've got a 1 times, and then I go up here and say, well, n is -1. I've got e to the j omega naught, or e to the minus j omega naught. K, again, is still a parameter of the equation. And then n up here will be, get my cursor to behave, -1. Okay, so again, by replacing this n with -1, I've looked up the signal and said it was height 1, and then this n with -1, I get this. And then I continue in the same way. So I say, well, next term is n equals 0. So when n equals 0, oops, I forgot something important here. I forgot this 1/6, so I have to put that in. So this will really be, let's see if I can sneak that in here. So 1/6 of that. So 1/6 times 1 times e to the minus j omega naught k times minus 1. So when n equals 0, let me put that in first. I have a 1/6. X of 0, I go up here and look, is 1. And then e to the minus j omega naught k times 0. Well, if n is 0, this whole exponent is 0 and the whole thing just stays 1. So I'll sort of simplify and say I have e to the minus 0 here. I'll simplify that more in a minute. And I go on to the n equals plus 1 term. Right, when I do that, I have x of 1, as again the value is 1. Oops, wrong button. Oh, I can leave that off for now. So I have 1, I have my 1/6 again. Can't forget that. 1/6 times 1 times, again, e to the minus j omega naught times k, and then n equals 1. So I put that in up here. And then I go on to my next term. So I say I've got n equals 2. And now I go up here and look and say, well, x of 2 is 0. So this term is 0. It doesn't even matter what's in the exponent. This whole thing is 0. And then the final term of the sum, n equals 3. And that's the same story, right? I go up here and look at the signal. I say, well, I've got x of 3, 1/6 times x of 3. Well, x of 3 is 0. So I can sort of put this all together now and say, well, I've got 1/6 times e. If I bring the minus signs out of the exponent, I have e to the j omega naught times k plus 1/6 plus 1/6 e to the minus j omega naught and k. Okay, so I've just taken this equation and dropped out all the terms that were 0 and simplified the exponent sum. And I can simplify it a little bit more if I group things differently. I can say, well, I want to put the constant out front, it turns out. Right, and then I'll have plus 1/6 for both of these, both this term and this term. So I can factor that 1/6 out front, and I have e to the j omega naught times k. Should be make it a little more clear. That's the lowercase k. And then plus e to the minus j omega naught plus k. So, and then we recognize the key thing now is the reason I grouped it that way is I want to look at this thing here. Let me sort of draw a blue bracket around it, right? It turns out this we recognize from Euler's formula. This is equal, just the part in brackets, not the whole thing, is 2 times cosine omega naught k. So let me bring that over to a new page to start on that. So when I make a new page here, when I put that together with what I already had, we've got to start again up here, writing an expression for a of k. I get 1/6 plus 1/6 times 2 cosine omega naught times k. Okay, and this is cosine of both of these. I should have them in parens. I can turn that into 1/6 plus 1/3 cosine. And now maybe is a good time to put in omega naught. So if I go flip back a page, I see my omega naught was pi by 3. So I can come up here and say this will be pi over 3. That's an awful 3. Fix that up some. Oh, too big an eraser. All right. Pi over 3 times k. And so now, this is my formula for a sub k. If I want to know the actual values, I have to go plug in, for that recipe, I have to go plug in one value at a time. So I do that now. So I say when k equals 0, I get, now I'll find, I'm looking for a sub 0. It's going to be 1/6 plus 1/3 times cosine. Well, when k is 0, this will be pi over 3 times 0 will be cos of 0, which is 1. And putting that all together, this is 1/6 plus 1/3 is 1/2. And just keep working my way through one period of k, right? We talked in class and you saw in the book, the discrete Fourier series is periodic, so I just need one period of it. In fact, it's going to be a little easier to evaluate some of these, I think, if I pull the 1/6 back out front. So I'm going to write it as 1 plus 2 times the cosine. And now omega naught is pi over 3 times 1. Well, cosine of pi over 3 is a half, right? So I can sort of just break this down a little bit to help those of you remember your trig. So this part, cosine of pi over 3 is a half. So 2 times a half is 1, plus 1 is 2. So I have 2 times 1/6, so that will be 1/3. And then here's a chance for me to make things efficient. Is that I could put in k equals -1, and the first thing I notice is, well, cosine is an even function, right? Cosine of minus pi over 3 is the same as cosine of pi over 3. So I'd still end up with a third here. And in fact, that's not an accident, because the Fourier series properties tell us, if I go back a page, that any signal, if this is my x of n, I should have labeled that from the start. So if this is my x of n, and it is real signal, real valued, and even symmetric around n equals 0, its Fourier series will also be real valued and symmetric around k equals 0. So that tells me that if I have this, a of -1 will be equal to a of 1 by symmetry. That's not always true, but on signals like this that are symmetric, so the symmetry of x of n. So that tells me that a of -1 equals 1/3. Moving along, I say, well, the next value, how about k equals 2? So if I want that, I can just go through and I say, well, when I'm evaluating that, I put in 2 for all the k's here. So I have 2 times 1/6 times 1 plus cosine. And now this will be 2 times pi over 3. So I have the cos of 2 pi over 3. But this, again, sort of stay with my color scheme. Cosine of 2 pi by 3 is -1/2. So that means I've got 1. Oh, what I lost in here was the 2. So it's 2 times the cosine of pi by 3, and then pi by 3 k, and k was 2. So that's this equation here, coming to here. If I have 1 And then the cosine is minus a half times 2 is minus 1. So these two cancel out, and I just get a 0 here. And the same symmetry argument tells me this is also equal to a of minus 2, right? So when k equals 2 or minus 2, the Fourier coefficient is 0. And the last one, k equals 3, I get 1/6 times 1 plus 2 times the cosine. And if I put in k equals 3 up here, I have 3 times pi over 3. So that gives me a cosine of pi. That's awful. I can do a better pi than that. Well, cosine of pi is minus 1, so I have 2 times minus 1 is minus 2. I guess I should stay with my practice here of saying, so this is minus 1, so 2 times minus 1 is minus 2. 1 minus 2 is minus a half, or minus 1, so minus 1 times a sixth gives me minus a sixth. So this tells me, if I put all these back together, it says if I want to make that square wave, I need 1/2 of the zero frequency, 1/3 of plus omega naught over naught and minus omega naught. I don't need any, because I have a 0 here, it says I don't need to mix in any of 2 omega naught or of minus 2 omega naught. And I need to mix in minus 1/6 of 3 times omega naught. So that's what my recipe is. Now I could go through and actually draw a sketch of this, although it's not going to tell me a whole lot of new things about the signal, but just for practice I say, well, and then it repeats periodically after that, if I wanted to do that. So, well, we can draw that picture. So let's go to a new page for that and say if I want to sketch it. And maybe it's worth drawing it to make one point, which is when I go to the Fourier series, I have a new independent variable. So now my horizontal axis is my k-axis, right? That's what is the independent variable for a sub k. So what I'm graphing here is a sub k. And if I want to do this, I'll try to keep it sort of to scale. See, so 1, 2, 3, 4, 5. I'll pick 6. So at k equals 0, I have a half. So at k equals 1, I'd have a third. And similarly, I'd have a third. So this is when k equals 1 and k equals minus 1. When k equals 2, I get 0. And when k equals 3, I have minus a sixth. This is my k equals 3 sample. And then it repeats periodically outside that. So I'll have another 0 at 4. I guess I shouldn't have put this so close. So I'm going to keep it going here. So if I continue my series, then my fifth sample, well, it repeats with the same period as the original signal. So what was at minus 1 is also at 5. So this will be 1/3 1/2, then 1/3 again. For samples, this will be 5, 6, and 7. And also, it's not just in one direction, it's periodic in both directions. So I have the same thing going on here. I'll have minus 1/6 here at minus 3. Another 0, right? So if I look here, move over 6. And so it just keeps repeating periodically outside of that. And then I guess at minus 5 it'd be the same as 1. So it'd be height 1/3 again. And I guess we're sort of beating a dead horse here, but keep going on and showing this. And again, the important thing is that this independent axis, I forgot to relabel it, is K. So I've transformed it, and that's why we'll see soon the Fourier transform, taking the system, taking the signal and finding the Fourier series as a form of transforming it. And again, this is like a recipe that tells me how much of each frequency. These are each basically multiples of omega naught. So this is how much of omega naught, 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught I need to mix in to make my signal if I want to make that square wave that I started with 2 pages ago. So it looks like this. Okay, so there's an example like we did in the class of doing the Fourier series. This one is helpful. The square wave is a very common one to get some practice with. And I will talk to you next time.